So welcome everyone to the February 2023 MIDAS webinar. I'm Harry Hockheiser, the director of the MIDAS Coordination Center. Today we're very pleased to have a presentation by Rob Trangucci. Rob is a PhD candidate in the statistics department at the University of Michigan, where he focuses on developing statistical methodology and missing data analysis and causal inference for problems in epidemiology, Bayesian methods for survey inference, and tools for quantifying how priors impact posterior inferences. He's going to talk to us about vaccine efficacy in a minute. Before I hand it off to Rob, just quick two things. Kristen, we have our next webinar in March. Which is the date? Is it the 24th or the 31st? Please let us know. Now we're at the end of the session.
Sure, it is the 31st.
The 31st. Okay, great. Thank you. So the last Friday of the month in March, and we do have 5 Fridays in March, so please be aware of that. The other thing I will say is just that we had a little bit of a glitch here. Rob can share his slides, but apparently can't make his video be seen, so we will get to hear but not see Rob. It's a little bit unfortunate, but I'm sure it'll be a great talk nonetheless. And with that, I'll hand it off. Rob, the floor is yours.
Hey, Rob, sorry to interrupt you, but I think I might have been able to figure out. Do you want to try to share your camera one more time?
It looks like it works.
There we go.
Yeah.
Awesome.
Here we go. That's great. Thank you so much.
Please take it away.
Okay. Thanks, Harry and Kristen, for inviting me today. I'm really excited to be here. So as Harry said, I'm Rob Trangucci. Today, I'm going to talk to you about some work with my advisors, Yang Chen and John Zellner, both at the University of Michigan. Yang is in the statistics department and John is in the Department of Epidemiology. And I'll talk to you about some new work in vaccine efficacy. So a quick outline of the talk. First, I'll walk through a bit about what vaccine efficacy is and how we define it. I'll get a bit more into detail in a thought experiment that sort of should clarify some things about our setting that we're focused on. I'll talk about our approach to the problem at hand, and then I'll talk about an application to clinical trial design. So first, I'm going to talk a bit about vaccine efficacy. I think it'll help to sort of put together a stylized causal diagram of vaccine efficacy. So we have a disease of interest that we're studying in a population at risk. And that disease is a function of some exposure to a pathogen of interest. And then given exposure, whether or not we observe that disease is a function of the susceptibility of the population to the pathogen once being exposed. And then vaccination ideally will reduce the incidence of disease in this population. Typically, we think of exposure and susceptibility as being unobservable to researchers. And so typically, people will focus on this total reduction in risk conferred by vaccination on disease. We'll use this diagram to think about this total effect of vaccine on disease. So vaccine efficacy is related to some health policy questions for vaccination, the most basic of which is, should we vaccinate people? And so the first few COVID-19 vaccine trials were aimed at answering this question. Should we vaccinate? It's really just a binary decision at the population level. And it focused on measuring this total effect of vaccine against symptomatic disease. And because these were clinical trials, we'll say that this total effect that was measured is called the vaccine efficacy against disease. You might have heard vaccine effectiveness, and that is different than vaccine efficacy, and that vaccine effectiveness is something that's measured in observational studies, sort of when the vaccine is licensed and deployed in the population. Vaccine efficacy is really focused on this clinical trial setting, which is the setting that we'll be focused on today. But I think it's clear to many that vaccine rollout policies can be improved with more nuanced information about vaccine efficacy. If you remember, we started the vaccine rollout in healthcare workers, frontline workers, and subsequently vaccinated older individuals. But I think there are still lingering questions as to whether or not the rollout could have been optimized given our vaccine set that we have. And so the sort of increased information about the sort of action of vaccination on disease can be thought of in two routes. Of course, disease is the physical manifestation of an infection. And so the first way that vaccine can prevent disease is by preventing this precursor to disease. We prevent infection. And so that I think is fairly understood. Another way that vaccines can prevent disease or reduce the risk of disease is given infection, the vaccine can reduce the risk of disease. So potentially it makes people less likely to become symptomatic, or it makes people less likely to develop severe illness, whatever the case at hand may be. When we think about policy making using models, these policy models need accurate vaccine efficacy estimates. So this is a figure from a 2021 paper investigating how to optimally vaccinate a population at risk in the UK via different vaccine efficacy scenarios. And you can see here that this first sort of flow from vaccinated into exposed, that's really a measurement of the vaccine efficacy against infection. Whereas these second arrows, the rate of the exposed population that becomes diseased or asymptomatically infected, that's really this conditional effect of vaccines' effect on disease given infection. And so that's all well and good, but it turns out that partitioning the causal effect of vaccine efficacy is a hard statistical problem. And it's hard for several reasons. The first reason is the fundamental problem of causal inference, as coined by Paul Holland. We see only one outcome for each unit. So we don't get to see what happens to individuals when they're vaccinated and the same individuals, what happens when they're assigned to placebo. We only get to see one outcome. Further challenge is that both infection outcomes and post-infection outcomes are measured with error. I'll talk a little bit more about that later. And then finally, this vaccine efficacy against post-infection outcomes is conditional on a post-treatment variable, namely infection. And so the reason that this is an issue, if we take this causal diagram right here, and we remember that I had exposure and susceptibility as impacting the incidence of disease in this population. Exposure and susceptibility also impact infection. And so when we condition on infection, we essentially subset the individuals that we're focused on who have been infected, that we've observed who have been infected in the trial. And we want to measure this dark red arrow, which is a causal arrow of vaccines' efficacy against disease. What happens is we induce these non-causal pathways from the treatment to the outcome through these unobservable states for individuals. So you can imagine if someone is immunocompromised and they might be more likely to become infected and more likely to become severely ill. And you can imagine that there might be more of those individuals in the set of people who are infected and vaccinated versus those who are unvaccinated and infected. And so that can bias our estimates of this, this arrow that we care about. So in 2006, there's a wonderful paper by Hudgens and Halloran that developed a solution using principal stratification. And I'll talk a bit more about what principal stratification is in a few slides. But this methodology has some limitations, as noted by the authors in their discussion. There's no measurement error in either outcome. So they assume that infection and a post-infection outcome like severe illness or hospitalization is observed perfectly. They assume that vaccine efficacy against infection is non-negative. So that means that they assume that no person can be infected when given the vaccine and uninfected when assigned to the placebo group. That might not hold for in an influenza trial where the vaccine is poorly targeted to the circulating strain, or if we were running a vaccine efficacy trial where we were comparing two different vaccines, we didn't have a placebo group. Potentially, we had a vaccine that's already been licensed, and we care about comparing outcomes to a different potential vaccine candidate. I'm not sure that we would make this assumption going into that trial. Furthermore, they focus on two treatments, which limits the usefulness of this methodology. And then it turns out that even with these restrictions, post-infection outcome vaccine efficacy is not identified. There's been more recent work in what's called the survivor average treatment effect. And this strain of literature is focused on understanding causal effects in situations where there may be informative censoring by death. So you can imagine if you're running an oncology trial, you care about how well a drug candidate reduces or increases the quality adjusted life years in those treated. Doesn't make sense to measure quality adjusted life years in people who have don't survive the trial. And so it's the same sort of mathematical situation as you would have for post-infection vaccine efficacy, where for people who are uninfected, you don't have a post-infection outcome. And you can see how the statistical work that happens in the survivor average treatment effects literature might not be applicable to this vaccine efficacy in the real world, because survival is something that is very well observed in clinical trials, whereas I think we're aware of the fact that infection is a very noisy intermediate outcome. So there's a 2011 paper in the survivor average treatment effect literature that shows that covariate information can identify principal effects, but this assumes perfect measurement, monotonicity, and two treatments. So our contribution is, first, we show that you can identify this vaccine efficacy against post-infection outcomes if you have an expanded set of covariates, even under the scenario where you have measurement error on infection and post-infection outcomes. And we don't restrict the causal model for infection. So we're not assuming any monotonicity. We don't assume that people are not harmed by the vaccine in terms of infection status. And then we also allow our results to be applied to scenarios where there are two or more treatments, which is another sort of novelty of our methodology. Furthermore, we can apply our method to binary, discrete, or continuous post-infection outcomes. The Hudgens and Halloran paper was really focused on binary post-infection outcomes. And we can show that our method can be used to design randomized vaccine trials to infer these estimates, this post-infection outcome vaccine efficacy. So before we go on, I just want to walk through some examples of post-infection vaccine outcomes or post-infection outcomes. You can think of them in the binary case. We have whether or not someone develops symptomatic disease, secondary transmission, of infection, severe illness or hospitalization, death. And then there are sort of continuous or ordinal measures that are also post-infection outcomes, something like a time to an outcome, like, for example, symptom onset, viral load given infection, symptom severity, and then antibody titer, measurement of antibody concentrations. So there are many post-infection outcomes that we might care about measuring and that we could plausibly be interested in how vaccines affect these outcomes. So, post-infection vaccine outcomes are common and of interest. Furthermore, multiple treatments are common in vaccine trials. So here's a 2008 vaccine run out of Michigan, where we have a placebo-controlled trial measuring the outcomes for a licensed inactivated influenza vaccine and a live attenuated influenza vaccine. And they wanted to measure the absolute efficacy. So that's going to be compared against the placebo arm, and the relative efficacies. So we're going to compare one vaccine against the other. And so this sort of design is common, especially will become more common for something like COVID-19, where we have a set of vaccines and there's interest in developing further vaccines. And so we also know that infection is imperfectly measured. PCR measurements are noisy. We have, typically PCR in the real world for something like COVID-19 is on the order of 0.6 to 0.8% sensitive. That's, there's a fair amount of error in PCR measurements. And while they're very specific, they do have lower sensitivity. And so a methodology for vaccine efficacy really does need to take into account the fact that we don't have perfect infection measurements. So now I'm going to walk through sort of a thought experiment where I'll define sort of in detail what principal stratification means and how it can help us in this problem. So imagine we have a randomized clinical trial. We're going to randomize treatment or vaccination, that's the syringe, or placebo, that's the syringe with the X through it. And we're going to measure infection or absence of infection in our trial population. And so this might be, one outcome of this trial that we observe. And we'll call this first row the infection, or we'll call the counterfactual infection under vaccination. And we'll call this second row the counterfactual infection under placebo. And we'll say that 1 indicates the presence of infection, and 0 indicates the absence of infection. And I say counterfactual because these are outcomes that we would observe for each person depending on which trial arm they were assigned to. So you can think of causal inference in this way, where each individual has 2 outcomes. You only get to see 1 outcome depending on how they've been assigned. In our thought experiment, why I'm calling it a thought experiment is it's going to be helpful to imagine that we can observe both outcomes in our in this case to help us think through defining principal stratification. So let's say we just want to measure vaccine efficacy against infection. How would we do so? So first, we're going to compare potential outcomes or counterfactual outcomes by individual. And so that's really important that we do this individual by individual, because when we think about the effect of vaccination on infection, we're going to compare the outcome for each individual. And we can see that the only thing that changes in this comparison is the treatment. So we're going to subtract the outcome under treatment, outcome under vaccination, from the outcome under placebo for each individual. We'll run through the study population until we get an expectation over these individuals. And you can see that this is this is really how we want to define causal estimands. It's going to be the expectation over a population of individual level causal effects. And then what we'll do for vaccine efficacy against infection is that we'll normalize by the expected infection under placebo. So it gives us sort of a rate of decrease or increase of risk under vaccination of infection. And you might be wondering, well, we can't observe causal effects in the real world, individual causal effects in the real world, because we can only see one outcome. What can we do? Well, expectation distributes over the difference. And if we have special, essentially randomization, let's call this capital Z randomization to treatment or treatment assignment. If we have treatment assignment that is independent of the potential outcomes, the potential infection outcomes, so that in sort of mathematical notation is this line, we can make this substitution whereby the observed infection for a certain treatment group is equal to the counterfactual expectation. And so in our observed trial, we can, or a real world trial will take the difference of these two quantities, and this will, in expectation, be equal to the quantities of interest here. And in our case, in this hypothetical trial, we'll have a 40% reduction in the risk of infection given vaccination. So we've gone through this example. We haven't talked about any post-infection outcomes. Principal stratification comes into the picture when we have a post-infection outcome of interest. In our case, let's imagine severe illness. We'll say severe illness under treatment is Y1 and severe illness under placebo is Y0. And again, we'll use ones and zeros to denote the presence and absence of severe illness. You might notice that there are some blanks in this table. Those blanks correspond to scenarios under which the individual is uninfected. And so if you are not infected, you can't have a post-infection outcome. And so we'll denote that scenario with an X. So one thing we might be able to do, you might be tempted to define a vaccine efficacy for severe illness with this estimand. So we have the conditional expectation of the outcome under placebo, given that someone has been infected under the placebo, and we subtract the conditional outcome of severe illness, or the conditional expectation of severe illness, given vaccination, given that they were infected under vaccination. So I'm going to show you why this is not a causal estimand. We imagine that our participants are indexed 1 through 10. That'll be I, our index. And if we look at the set of individuals who are infected under placebo, that's the set 1, 3, 5, 6, 7, 8, 9. If we look at the set of individuals who are infected under treatment, that's the set 1, 3, 4, 6. And this sort of highlights the fact that there are different groups of people included in each of these expectations. So any difference that we observe in these in this quantity is explainable by the fact that there are different groups of people in these groups. So so we can't use this as a causal estimand because it's not a comparison of individual outcomes under treatment and control. It's really a comparison of different groups. And so the people in this group might have a different expected value of under placebo than people in this group. And that would sort of bias our estimate. So that is not a valid causal estimand. But what you might notice is that we can group individuals by their outcomes, their infection outcomes under treatment and control. This is the group that's protected, for whom under treatment or under vaccination, people are not infected, but under the placebo, they are infected. And we can define a group as just the concatenation of these two outcomes, outcome under vaccination and outcome under placebo. And we'll call this grouping the principal stratum. And then for the protected principal stratum, we'll define the conditional expectation of the outcome under placebo. There's only one severe illness outcome for this group, and that's under placebo. We can do the same for the harmed stratum. And apologies, my daughter is here, and so if you hear a baby in the background, that's her. So we have our conditional expectation of the severe illness under treatment. And then we have the always infected stratum. And this is a group wherein we have treatment, we have outcomes under treatment and placebo. And this is the group in which we can define our causal estimate of interest. We have conditional on being a member of this always infected group. We can define sort of a valid causal estimate, a valid causal comparison between outcomes under placebo and outcomes under treatment. And so this is the sort of causal estimate of interest that we're going to focus on. Now, we would estimate this if we have randomized treatment assignment that's independent of both infection outcome and post-infection outcomes. We can make this substitution again, that the observed expectation given a treatment arm is equal to the counterfactual outcome of interest, the conditional expectation in the estimand, in the causal estimand. But the issue is that we don't observe both outcomes, of course. We have this fundamental problem of causal inference. We only observe one outcome. And so we're sort of left scratching our heads a bit. We can't define which group each of these individuals is in with only one infection outcome. And mathematically, this comes from the fact that this joint distribution has 7 degrees of freedom, whereas the observed, so that this is the sort of counterfactual distribution, and the observed data has only 4 degrees of freedom. And so we won't be able to identify all the degrees of freedom in our joint distribution in order to learn the causal estimate of interest. So just to do a recap, principal stratification allows us to define causal effects that are conditional on post-treatment outcomes, but these estimands are not typically identified under very general conditions. And so I've been talking about what do I mean by identified? And this first line is just a formal definition of identifiability. I think we'll focus on the informal definition. If every data set from a model F alpha, that's just like a family of distributions that's indexed by a parameter alpha. If every data set from this model maps to a unique parameter alpha, we'll say that the model is identifiable. And this property undergirds a lot of asymptotic theory. And it's useful to understand what parameters may need informative priors or what parameters may be sensitive to priors. So I mentioned that the survivor average treatment effect literature had, and sort of other principal stratification literature has thought about how do we identify principal stratum effects. And there's a 2016 paper that shows that if we have a trial that's run independently across study sites, we can identify principal effects, and that if we have covariate information, this 2011 paper, as I mentioned, this can also identify principal effects. Both of these achieve identification under monotonicity and perfect observations. And so we assume that there are no harmed individuals in this monotonicity assumption. Now let's walk through to our approach. And so we're going to just talk about the causal. We're going to talk about the causal diagram first. That's going to encode our assumptions about the data generating process of interest. As I said, we have vaccination, and principal stratum is an unobservable latent random variable. We'll have observed infection, and that's going to be a observation of a noisy state, or a noisy observation of a underlying unobservable state, infection state S. And you'll notice that this is a non-differential measurement error model. And we'll also have observed disease that is, again, non-differential measurement error of a true unobserved disease status Y. And that really just means that everything that you could, all of the information about the distribution of our observed disease and our observed infection is contained in the observed, or the unknown state variable. It's a sort of a typical measurement error assumption. We expand this causal diagram by, we take advantage of the fact that most vaccine efficacy trials are run across multiple study centers in order to recruit many different patients. And so we'll say that the study site impacts the distribution of principal strata. And we'll also imagine that we can measure a pre-treatment covariate that is caused by the principal stratum, and that can also impact the post-infection outcome. So some things to note about this causal diagram before we move forward. So we have randomized treatment assignment. So that means that vaccination is going to be independent of principal stratum. It's also independent of the joint distribution of our post-infection outcome. And another sort of assumption that's encoded in this graph is that given principal stratum, the study site is independent of the distribution of the pre-treatment covariate. That's another important assumption for our method to give us identifiability. Finally, we assume that given principal stratum, the distribution of the post-infection outcomes is independent of the study site. And so that is a key assumption for us. And that's, something that we might want to investigate further in a sensitivity study. So this is a main theorem of our paper. We'll suppose that this previous directed acyclic graph describes the data generating process. Furthermore, if we have the sensitivity and the specificity of the infection outcome test, if that lies, they both lie in the interval 0.5 to 1, and we have the number of study centers is greater than or equal to 2 to the number of treatments under study, and the number of levels of the discrete covariate A is greater than or equal to 2 to the number of treatments minus 1, then we can identify this joint distribution of principal strata and covariate levels given the study site, and we can identify the post-infection outcome distribution given a principal stratum and a covariate level K, if this is identifiable up to a multiplicative constant that's dependent on an unidentifiable parameter, that is the sensitivity of the post-infection outcome. And it turns out that vaccine efficacy against post-infection outcome is identifiable strictly because this unknown parameter dependent on sensitivity of Y partials out. So the principal, so I just want to do some compare and contrast of our principal strata methods. So Hudgens and Halloran really could stand in for any principal stratification method, but we'll use it just as a in order to draw some comparisons right now between the methods. So we don't have restrictions on our principal strata. We allow for noisy infection and post-infection outcomes. We can apply our method to any number of treatments, and our method extends to continuous or really any secondary outcome measurement. I wanted to essentially show that we could use our model to design a clinical trial to infer these estimands. So I'll imagine that we have a two-arm vaccine trial. We're going to simulate data under a null distribution and an alternative hypothesis. And we're going to measure the type 1 error and the power of these in these scenarios. So our decision criteria is going to be that we want to pick vaccines or pick a vaccine that has a vaccine efficacy against infections of greater than 0.3, the vaccine efficacy against severe illness of greater than 0.1. This mirrors the Pfizer COVID-19 trial criteria, where they were only essentially rejecting the null when the posterior probability of vaccine efficacy against symptomatic illness was greater than 0.3. We'll target a power of 0.8 when vaccine efficacy against infection is 0.5 and vaccine efficacy against severe illness is 0.6. Again, this mirrors the Pfizer trial in that we're targeting a power of, they were targeting a power of 0.9 when vaccine efficacy against symptomatic illness was equal to 0.6. And we'll say that our covariate A is baseline antibody concentration. And we'll say that there are 3 levels of that. And we'll assume that we have a clinical trial that's run across 4 study centers. So that meets our criteria for identifiability. We'll also include a categorical covariate that's a proxy for age group with 3 levels. And we'll measure infection and severe illness as our outcomes. So that leads to a data set that comprises sextets for each individual in the trial. We'll have noisy infection, noisy post-infection outcome, treatment assignment, study site, membership, this covariate or baseline antibody concentration, and then age group. We'll do, and we did full evasion inference and STAN. And then our decision criterion is we reject the null hypothesis when the posterior probability of vaccine efficacy against infection and vaccine efficacy against severe illness is greater than 0.9. The left-hand side chart shows the type 1 error. So this is the probability that we reject the null hypothesis when the null hypothesis is what generated the data that we've observed. And in our case, the null distribution that we're generating data under is a vaccine efficacy against infection of 0.5, but a vaccine efficacy against severe illness of 0. And so you can see we control the type 1 error with this model. We also are investigating our model under two scenarios. So one in which we perfectly observe the covariate A, and another where we have a noisy proxy for the covariate A. And we're assuming non-differential measurement error for this noisy proxy. And you can see the blue corresponds to the perfectly observed covariate, red corresponds to the noisy proxy scenario. So on the right-hand side, we have the power. And so this is these are the proportion of trials that reject the null when the alternative is true. And that alternative, again, is vaccine efficacy against infection of 0.5 and vaccine efficacy against post-infection outcomes of 0.6. And you can see here that generally having the perfectly observed covariate leads to higher power, which makes sense. And one thing I want to focus on is the sample size here on the y-axis. This shows that we reach our sort of nominal power at a sample size of 40,000. So that essentially corresponds to the sample size of the Pfizer COVID-19 trial, which was run at about 4,200 participants. And so I'm showing here that we can use our method to design sort of reasonably sized trials. And we simulated the data under a sort of scenario that sort of mimicked some of the COVID-19 trial. Operating parameters. So I'm gonna wrap up here soon. So just to go back over our contribution, we show that the vaccine efficacy against post-infection outcomes can be point identified if we have these discrete pretreatment covariates. And those pretreatment covariates are, again, study center membership and a pretreatment covariate, discrete covariate that's related to the principal stratum. And our results generalize to multiple treatments. This is important for future COVID-19 vaccine development. In the paper that I'll provide a link to at the end of this presentation, you can go and see that we've run a simulation study with 3 treatments. And we show that it's possible to actually size trials to infer post-infection outcome vaccine efficacy. And so the sort of immediate implication of our method is that it's applicable to the survivor average treatment effect estimation, which might be useful in non-vaccine efficacy settings. And it's a very straightforward to extend the methodology to, instead of binary intermediate outcomes, in our case, infection, we could do intermediate or categorical intermediate outcomes, which would allow us to apply our method to non-compliance in multi-arm studies without requiring an exclusion restriction, which is a sort of novel application and a novel statistical model for principal stratification. Something that I'll work on in the future, and I think is necessary to really make this methodology most useful, is to develop a sensitivity analysis for deviations from these key assumptions. And as I said, these key assumptions, the sort of most important one is that we have this conditional independence of the covariate and study site, namely that the covariate distribution is independent of the study site. This study site or study center homogeneity, where the joint distribution of the post-infection outcomes is independent of the study center, and this non-differential measurement error, which might hold in certain settings, but in other settings, we might not assume that holds. So we have our paper up on archive. Please go check it out. I'd love to hear some feedback if you have any. And for this this work, we've been funded by a U01 grant at the CDC, as well as some funding from the Simons Foundation. We have a bibliography here if you're interested in some of the sources, and I'm happy to take questions.
Great. Thanks, Rob. Nice talk.
Thanks.
Do we have any questions from the audience? Please fire away. Feel free to put something in the chat or the Q&A. I will start off by sort of asking a question here and saying that I know nothing about clinical trials. This is way outside my depth, but I'm just sort of curious about something that without getting into the really some of the political issues that have come up with COVID, it seems that there is likely to be the possibility in future vaccine trials that the population you're going to get at any center may differ from who will be part of a trial will differ from the people you hope to get into the trial and to get eventually to get the vaccine. And I'm wondering how that might play out in this sort of stratifying model, or is that a whole other can of worms?
No, it's a really good question. I think I think that's either an extension or sort of a different problem to tackle for causal inference. I mean, that would lead to issues even just in inferring like the infection vaccine efficacy. And so I think it's a really important question. How do you, that's what's called transportability in causal inference. How do you take a causal estimand that you've learned in one population, transport it to potentially a different population? And I think oftentimes the solution is modeling the causal estimand as being conditional on observable covariates, and then barring the sort of reasonable assumptions on that you can really define selection into this study conditional on covariates, you'd need to do sensitivity analyses to understand how the causal effect might differ in this different population. I think something that could help is collecting information on exposure, sort of behavioral attributes, because like vaccine efficacy estimands are really dependent on distributions of exposure in the treated and untreated groups. So if you expect that the distribution of exposure will be different in some population, it's important that you define either some like biological model that can help transport this estimand. It's something that I've been thinking about. So that's sort of off the top of my head, but it's a really good question.
So there's the postdoc work for you, right?
Actually, I'm going to be I'll be a tenure track in the stats department at Oregon State University next year.
Great!
So,
well, congratulations.
So that'll be. Thank you so much. Yeah, that'll be my
first project.
My first project. Yeah, exactly. Yeah.
Great. Any questions from the audience? Please jump in here. I will throw something out if I don't get something in a few seconds, but we want to make sure that Rob feels like his comments here are valued. So I guess the other thing that we've sort of learned here that might have been unfamiliar for previous eras of vaccination is this possibility here now of the loops here, where you get people who have multiple vaccinations and multiple infections, perhaps. And I'm just wondering if that sort of cycle, which is really not familiar from prior outbreaks and prior vaccinations, if that poses any complication, or is it possible to use any of these approaches to, say, model the value of, say, the proposed policies? Like, should there be more boosters for people, and when? Is this sort of approach helpful for that?
I think we need to expand on this approach. I think you could potentially like collect pre-treatment covariates that would allow you to come up with like stratified causal estimands and causal estimates. And so that's, you could imagine doing, so that the sort of like proof that we have in the paper is totally non-parametric. So you could learn a causal estimand in, say, people who have been vaccinated more than once, people who have been boosted, people who have received 2 boosters. But it also, like, there are sample size considerations, because as you increase those, the dimensionality of your covariates, you're going to need to, include more people. So I think you run into a sort of just sample size problems or problems with running your RCT in the real world. And so potentially need to make some modeling assumptions that will improve your power. But yeah, that's another good question. I don't have a straight answer for you, but that's something that we'll need to.
Yeah, that's okay. Yep. We do have a question in the Q&A here that I'll read out to you. How would you test that you were getting enough heterogeneity by center for this approach to work?
That's a good question. So the proof is dependent on there's a sort of a you need essentially that the matrix of distributions over principal strata by study site is full rank. And so you could run your procedure, you'll come up with inferences for principal strata distributions by study site, and you could measure like the condition number of that matrix, which would give you a sense for how close your method is to being not full rank. So yeah, that's another sort of topic of further study, is to understand. I mean, like this is really you'll see the papers is really focused on identifiability. So we have like very strict identifiability conditions. The question is, when you're in identified regime, how do you think about variance of your estimators? And the variance of the estimator is really dependent on this condition number of the distribution over principal strata by study site. I don't know if that answers your question.
Well, we've got another one here.
Okay. Yeah.
From Brittany Morgan. Great presentation. My question is rather simple. How computationally demanding is this approach for investigators compared to more traditional frequentist vaccine efficacy methods?
It's very computationally efficient. Everything is implemented in Stan, so that Stan code gets compiled down to C++. You really need like cross tabs. Let's assume everything is discrete, like your covariates that are not related to this A covariate. If we think about age group, then you really need a cross tab of outcomes by age, by let's say you wanted to do by race, by study site. And it turns out that the proof is really not dependent on Bayesian versus frequentist. And so you could do a maximum likelihood estimator if you preferred not to use Bayesian methods. And so that would be, you'd run your favorite, optimization algorithm to find a maximum likelihood estimator, which should be very efficient computationally, and Stan is a very computationally efficient language, and so I'll have code up soon which implements these models. They're pretty straightforward. Thanks for the question.
Fantastic. Do we have anybody else? Any final questions here for Rob? Okay, well, hearing none, I just want to thank Rob for a really nice and interesting talk, and I know for me at least a window into a world that I don't spend much time in, so really appreciate it. I also want to encourage folks, if anybody's on who is a trainee, grad student, or postdoc who's in a similar position to Rob, and you've got a story you want to tell, this is a great venue to tell it. And so please don't hesitate to get in touch and ask if we've got some slots coming up. We're pretty well set through most of the spring into the summer, but we could always use some more for the fall and following. So once again, we'll just close out by saying thanks, Rob, for a nice talk, and great luck with your new position. And we'll see everybody on March 31st.
Thanks so much.
Thank you all.